Prove, using the formal definition of convergence, that the sequence 1, 1/2, 1/3, 1/4, and so on is convergent. So let's remind ourselves of 3 facts that are going to help us along in this formal proof here. So 3 facts. The first 2 facts I've proven in separate videos. So the first fact is if A is strictly greater than B, if A is strictly greater than B, A and B are just real numbers, then this implies that 1 over A is strictly less than 1 over B. This is pretty much just saying if I have 2 fractions with the same numerator, or just 2 fractions with a numerator of 1, but that you could also generalize this to 2 fractions with the same numerator and different denominators, then the one with the bigger denominator is the one that's smaller. So, for our second fact, this is really important for this particular proof, given any epsilon greater than 0, any epsilon as close to 0 as I wish, there exists an n in the positive integers. Shorthand for positive integers is writing a bolded z here with a plus on the bottom. There exists an n in the positive integers such that 1 over n is strictly less than epsilon. Again, I've proven this fact 2 and fact 1 in separate videos that I've linked in the description and the eye icon in the top right corner here. And our third fact, which is really just a statement, that the usual distance metric defined on the real numbers is the following. The distance between any 2 points A and B is equal to the absolute value of the difference between those 2 values. Okay, so now we're ready to start. Now we're primed to prove this statement formally. Okay, first of all, if you want to show that this sequence is convergent, we have to show that it converges to some value. So let's think of a candidate value that this sequence converges to. Well, obviously, if you've seen this before, we know that this converges to 0, but let's think about why that would be a good candidate if we had never seen the sequence before. Well, because given any positive number as close to 0 as we wish, I'm always going to be able to find a number of the form 1 over n, which is exactly the general term in our sequence. We could rewrite this sequence as 1 over n from n equals 1 to infinity. And so I'm always going to be able to find, in other words, an element in this sequence that is strictly less than that positive number. That means that if I were to choose any number strictly greater than 0, then I would always be able to find an element in the sequence that is less than that number. So it makes sense for us to choose 0 as a candidate value for the point to which this sequence converges. So let's prove that that sequence converges to 0, therefore proving that that sequence is convergent. So claim our sequence 1 over n from n equals, not n equals 0, n equals 1 to infinity converges to 0. Converges to 0. Now, check this out. So we want to prove that given any epsilon strictly greater than 0, there exists a positive integer capital N, such that the distance between p and p sub lowercase n is strictly less than epsilon, whenever n is strictly greater than n. So check this out. I know that given any epsilon strictly greater than 0, there exists a capital N in the positive integers. This is by fact 2. There exists a positive n in the positive integers such that 1 over n is strictly less than that epsilon. And check out this other fact that is due to fact 1. So I'll say due to fact 1, if n is strictly greater than n, then 1 over lowercase n, I should say if lowercase n is strictly greater than uppercase n, then 1 over lowercase n is going to be strictly less than 1 over uppercase n, which is strictly less than epsilon, implying that 1 over n is strictly less than epsilon. Now, by fact 3, by statement 3, if we're going to use the standard metric that's usually defined on R, the real numbers, by statement 3, the distance between 1 over n, which is our general term in our sequence, and 0 is equal to the absolute value of 1 over n minus 0, which is equal to the absolute value of 1 over n, which is equal to 1 over n, since n is positive, therefore 1 over n is positive, which is strictly less than, check this out, which is strictly less than epsilon. This is the defining move for this proof here, or this is probably the most important part of this proof, or maybe not the most important part, but this is what finishes out the proof rather. So this distance, 1 over n, is strictly less than epsilon, as we've just shown, whenever, because I just said if n is strictly greater than n, and remember there exists an n and z such that 1 over big N is strictly less than epsilon whenever, so check this out, whenever n is strictly greater than n. So I've cleared the board to show you this last little thing that we can do to finally convince ourselves that this sequence converges. So we're going to progressively write this statement that we've derived, the statement that I cleared the board, the statement that we wrote down before I cleared the board. We're going to progressively rewrite that statement so it exactly corresponds with the formal definition of convergence. So we derived that given any, or we rather proved that given any epsilon strictly greater than 0, there exists an n in the positive integers by fact 2, such that 1 over big N is strictly less than epsilon, and by fact 1, 1 over little n is strictly less than 1 over n, which is strictly less than epsilon, whenever n is strictly greater than big N. So therefore, since this fact is true, we can rewrite this and get a little closer to so that this exactly corresponds with the formal definition of convergence, so that we can really convince ourselves that this sequence converges. We can rewrite this as because this is true, given any epsilon strictly greater than 0, there exists an n and z plus in the positive integers, such that 1 over n is strictly less than epsilon whenever n is strictly greater than n. Therefore, that is because this fact is true. Because this fact is true, we know that there exists an n in the positive integers that has this property, such that 1 over little n is strictly less than epsilon whenever little n is strictly greater than big N. So therefore, since the distance we've shown previously that the distance between 0 and 1 over n, we've shown that this distance is equal to 1 over n. Therefore, we can say the following: given, let me change colors here for our final statement that exactly corresponds with the formal definition of convergence. We can say that given any epsilon strictly greater than 0, there exists an n in the positive integers, such that since 1 over n is equal to the distance between 0 and 1 over n, such that the distance between 0 and 1 over n is strictly less than epsilon whenever n is strictly greater than n. And hopefully this sequence of rewriting this statement, this cruder statement, this sequence of rewriting the statement and showing how we rewrote it, makes it more clear that this sequence converges.